record. Okay, so in the study guide, the first page is just all the stuff about sequences. All right, don't confuse a sequence with a series. Okay, they're very different. Series have the summation sign. Sequences do not. Sequences are just the list, and really the only test you have for sequences is the nth limit test. If you can't take the nth limit, right, we had a lot of tools we could use. Sometimes we use L'Hopital, sometimes we had to use the squeeze theorem, right? And then we also had the absolute value theorem, right? If you had an alternating sequence, we could try taking the absolute value, and then that would prove that the limit went to 0. I also gave you one additional way you could show something was going to converge, and that was like if it was bounded and monotonic. So we know if it was constantly increasing toward a value or constantly decreasing toward a value. So this is a useful idea, but it's not necessary if you understand this concept. But if you try to claim something's bounded, you've got to tell me what it's bounded above or below by. Now, if we have that sequence, remember that was alternating between 2 and 4. Well, it was clearly bounded above by 4, bounded below by 2. But if you had something like 1 over n, right, well, we could say, well, it's approaching 0, so we could definitely say it's bounded below by 0, but it's never going to reach 0. So make sure when you say we understand bounded, you just have to have a value. It's almost like finding an asymptote on a graph, right? You just have to find a value that you know the numbers are never going to cross that value. And that's so it's not specific. You don't have to find the closest possible value you can, but if you can just demonstrate that it's bounded. So this isn't used a lot, but it's really helpful when you have things like factorials or things that it's not easy to algebraically take a limit of. This is just an alternative way to maybe look at stuff. The second page, I've got your commonly occurring limits. So if you recognize any of these limits, you're allowed to just cite them. Don't forget that x in all these limits represents a constant number. So you're never going to see an x in the problem, right? So for example here, we might have 1 plus 2 over n, right? And then that would mean that this is e squared, right? And I also, in your notes, pay a close attention to this one. Remember, we can disguise that guy, right? By combining that into one fraction, we can flip it upside down. So in your notes, I showed you alternative versions. So you have the added advantage this semester of being able to literally go back and watch anything from class you need to watch, because all the lectures are on YouTube. So if you want to review a concept, or you're studying, or you don't understand something, you can literally go back and watch me reteach it and work the examples. So there is some benefit to all the crazy stuff we've been dealing with this semester. All right, so series, right? We talked about partial sums. If you can look at the sequence of partial sums, we know that that's one way to figure out what the sum is going to be. There are really only 2 series that we can really ask you to sum, and those are geometric and telescopic, right? So every other series, we can't really sum it, we just know a sum exists or not. So if we ask you to calculate the sum, I'm not going to ask you to give me the sum of something you can't calculate. That should be a big clue that you're probably looking at one of those 2 types of series. And remember, you may have to rewrite the series to make it look like the standard form of a geometric so you can sum it up. Pay attention on the indexing, right? Because if we use that formula, a over 1 minus r, you got to be counting from 0. But on the quiz, we did problems where we counted from 1, and I was like, well, the easiest way to do it is sum it from 0 and then just back out the first term that you don't need. Okay, so make sure that you're paying attention to subtleties like that. These are some algebraic properties of limits, all right? Then the next page is that handout I gave you guys early in the semester where it just had the guidelines and then the chart on the back. And then the last page is all about power series. So once again, when you look at these power series, right, you can see the center of the series in the formula. So it should be x plus or minus something. If there's nothing attached to the x, we know it's centered at 0. If we have a value attached to x, we know it's centered at c. And then I've got on here how to do your test for convergence, right, what the pictures look like. And at the bottom, I've got here the algorithm for generating a Taylor series, right? And then I've got a table here of a lot of really common Taylor series. So a good exercise is, these are all very easy derivatives to calculate and compute. Well, down to like arctan and arcsine, right? But these guys are all pretty easy to compute. It's a good practice to see if you can generate the series because you know exactly what it's supposed to look like when you're done. So you can practice generating them from scratch. And then another neat trick to do would be like, well, take 1 over x and integrate it to get ln of x, right? So there's a couple different techniques we saw that you don't have to build every series from first principle. And I am definitely going to give you something and ask you to build it off something else. So if you recognize relationships between some of these functions on here, we can do that. You could integrate cosine to get sine, right? Because derivative of sine is cosine, right? We could, if I gave you sine, you could take the derivative of it to give me cosine. So, I mean, there's a lot of cool, clever ways. You don't have to follow the algorithm from first principles to generate a series. All right? Cool. All right, so what do y'all have for me? And because of the camera, I'll have to repeat the question. What? Any conceptual questions? Kind of. Like, I mean, I might have some stuff where I might add, well, it's not really like the integral test where I could say set up but don't evaluate. But, I mean, yeah, there could be some conceptual stuff on there. I could maybe ask you, like, a general question about a sequence or a series, or, like, what test do you perform? Like, I may do a multiple choice or something like I did with the integrals, where it's like, give me the technique without actually having you work it out. Can you recognize the elements in or something like that? But it's possible, yeah. I'm still tweaking the test. Yeah.
Will there be a word problem like sounds of multiplication?
Will there be a word problem? I don't know. Probably not, because there's just so much stuff to worry about in this unit that I just don't know that I'd have time to be that creative on the test. So, because I want to hit as many different topics as I can, so it just might not be possible to do like a word problem. But yeah.
Can you go over some of the tests and just like what kind of tells you would be able to look for?
Yeah. So, the tests and the tells. Okay. So, remember, for those of you that have come to me in Milledge Hall and we've actually seen this happen, right? The first thing when you're talking about series now, right, not sequences, a sequence can converge to any value. All a sequence we're saying is, what is the list approach, right? What does the list turn into eventually, right? But for series, if that limit of that term does not go to 0, it's never going to converge. So the nth limit test will test for divergence, but it does not test for convergence. So you should always be able to like eyeball that at the beginning, because if you can see that the limit's non-zero right up front, you can simply state the limit of this does not equal 0, it diverges, and you're done. You get to stop the problem right there. So at this point, you should be able to kind of visualize some of these limits. The geometric series, you want to look at obviously something r to the n, right, or some value being raised to the n, but don't think about that in combination with any other elements, right? A geometric series doesn't allow for factorials. It doesn't allow for other stuff. So if you have a bunch of stuff raised to the n, you want to combine it all, right, to the n, and then look at what's inside. And if the stuff inside, if the absolute value is less than 1, we know it'll converge. If the absolute value is greater than 1, we know it'll diverge. So if I gave you a series that was like something like 2, right, times 4 to the n, right, over 6 to the n, when we know we could write that, right, like that. So now I have a geometric series, and that fraction is in fact less than 1, so we know it could converge and we could complete. We could even simplify it down to 2/3 if we wanted and look at it there. P series. Don't ignore P series. A big clue, a P series technically is only like this. Oh, and guys, there's a typo on here. I just forgot to tell you. I mentioned it when I did it last time. This should say P is greater than 1, because it does allow for non-integer exponent. So if it's 1 over like n to the 2, right, well that's clearly a P series. But if you're trying to do a comparison, or you're suspecting something converges or diverges, whenever you're in a situation where you've got polynomials on the top and bottom, or everything's just powers of n on the top and bottom, when we look at the highest power in the numerator, the highest power in the denominator, we simplify and then we compare to that P series, okay? So that's a big tell. Telescoping, right? It's usually the subtraction of two things, but we did an example where I said that we could have, you know, the product of two things. So I'm not going to put anything that requires partial fractions on this exam because too many of all the transfer students just never really learn partial fractions properly. So it will be on the final because by then they will have been able to review it, but I'm not going to do anything that requires partial fractions on this particular test. But a lot of times we hide telescoping series in plain sight. You can just use partial fractions to separate. If you think you've got one, you want to list out the first handful of terms and see the pattern, right, of elimination. And then you can kind of see what's up front on the front end versus what's left over on the back end. But just like a telescope, everything in between should collapse and go away. So you should kind of end up with the first term and the last term, and then that's why we can add them up. That's why we can sum these two. The integral test. So remember I told you guys that I'm not going to hold you responsible for the actual proof of a p-series. But if I say, show me that this p-series, like 1 over n cubed, show me that it converges, right? What do you have to do to show that it converges? What test proves a p-series converges? The integral test, right? So I'm not gonna like make you do the general integral 1 over n to the p. We did that in class and we broke down and saw all the different values of p and why it converges or diverges. But if it's just a general, does it converge or diverge question and you recognize a p-series, you can say p-series where p equals this and it converges or diverges. But if I say prove to me, I'm going to actually give you a specific p-series so it's easy to integrate, but that's what you do. Use the integral test to show it converges or diverges. So if you don't remember improper integrals, I did a bunch of those in class when we did that section and I showed that. The integral test, it's really going to be used when it's something you can write as a function of x that looks easy to integrate, right? If you just can't think of any other tests, I kind of slide that one down to the back burner, but a lot of the natural log stuff is usually going to require the integral test, right? So look for natural logs. Those are usually, because we can't really integrate them directly, but we can usually differentiate them. If you have natural log of n over n, well, the derivative of natural log is 1 over n, so you can use a u substitution. You can integrate that very, very easily. When you do the integral test, sometimes it involves e, right? Sometimes it involves natural log. Be careful of negative exponents because that was the one thing everybody screwed up on test 2, was when you finish the integral perfectly correctly and you got e to the negative 1 or e to the negative 2, when everybody took the limit, they said that went to infinity. So if you have a negative exponent, rewrite the equation and make all the exponents positive, right? You know, you can do that by just crossing the fraction bar. So if you saw e to the negative 2, everybody read that as e squared when they took the limit and said it went to infinity. But e to the negative 2 is 1 over e squared, and that went to 0. So everybody kind of messed that up. Sorry, not negative 2, it was negative b, because you were taking the limit as n went to infinity. So just as a general rule, I always eliminate all negative exponents when I'm actually calculating the limit. The only time I make things negative is if I'm taking a derivative and I want to use the power rule, but as soon as I'm done, I immediately put them back to make them positive, because if you can't see what's on top or bottom, that'll screw you up. The ratio test can be used a good bit of the time. Remember, that's how we prove or find the radius of convergence or find the interval of convergence. We always use the ratio test on those functions. But factorials, anytime you see a factorial, the ratio test should be your go-to, okay? The root test. The root test, you're gonna take the nth root. Be careful, because I saw people doing this. If you have, right, something like n to the 2n, you need to write that like this, because the root test does not allow you to take the whatever nth root you want. You can only take 1 over n. So you have to separate out the stuff, the n, from everything else. So now if I took the nth root of this, I would end up with n squared. Okay, so people were doing that wrong. I saw a lot in other classes when they were studying for their exams. So the root test, you should just have a ton of stuff raised to the n. Okay? Because, and the whole point of it is you want to wipe out that exponent. If you don't have stuff raised to the n and you try to do the nth test, then you're going to end up with things like 2 to the 1 over n, right? And who remembers those limits? Most people don't. Okay, so you want to be careful when you're using the root test. The direct comparison and limit comparison. The direct comparison is a little bit trickier, right? Because you have to, not only do you have to set up an inequality, but the inequality has to run the right way. So if you're proving convergence, you need to find something bigger that converges. And if you're proving divergence, you have to find something smaller that diverges. And so it can be really tricky to get those right. The direct comparison, though, is actually quite useful when there's like sine and cosine involved. Because sine and cosine, we know, bounces between 1 and -1. So it's easy to set up the inequality for that because we can see the bigger side and the lower side. Limit comparison is a little bit more robust. It's a little bit easier. It's kind of harder to screw up because all you're doing is comparing it to a thing, and it doesn't matter if that thing's bigger or smaller. So limit comparison works great when you think you've got some version of a p-series. Right? So all you're going to do is compare it to the appropriate p-series. So whenever we're looking at polynomials, whenever we're looking at polynomial over a polynomial, that's what I was saying. You take the highest power in the numerator, highest power in the denominator, simplify it, and that's what you want to limit compare it to. Remember that roots are just exponents. So if you see the square root of n, that's n to the 1/2. If you see the square root of n squared, that's n to the 2. Square root of n squared would be n, but if you see the cube root of n squared, right, that's n to the 2/3. So you can use those powers. The p-series does allow for fractional exponents, so make sure you're doing that correctly. More than one test will work. I'm pretty open-ended on the test. I don't get specific until you use this specific test. I just say, tell me if these things converge or diverge. But I am pretty good at writing series where only 1 or 2 tests really do work. So, you should be looking for the tell to kind of lead you in the right direction. Yeah.
If we recognize a series, can we go ahead and say if converge or diverge? You still want us to show proof for it?
You don't, you have to justify your answer, right? You can say it converges or diverges, but that's a coin flip because anybody could go down the test and guess converge or diverge. You just have to do something to justify your answer, whether that's perform a test. If you want to write me an explanation as to why in words, that's okay. But remember, when we did these problems, we had a lot of different ways we did this. If you wanted to cite, but like if it's something like you're saying, well, it's so let's look at something like this. Let's say if I had the series from 1 to infinity right? Something like this, okay? Well, if you try to tell me, oh, this converges because it's just a p-series 1 over n squared, that's not really correct. I want to see the limit comparison test. I mean, it's an easy test to perform, right? So if you recognize, right, if we wanted to compare this to, right, the highest power of n in the numerator, the highest power of n in the denominator, that simplifies to 1 over n squared. So then the limit comparison test says we'll take the infinite limit of the original thing over the thing you're comparing it to. Well, that's going to flip that fraction. So when you distribute and then I will allow this, right? When you're doing infinite limits, I will allow you to say that this is equal to the limit of the highest power of n in the numerator, highest power of n in the denominator. So that guy is 1. So since this is greater than 0, we know they both converge. And when you're doing the limit comparison test, you have to know what the thing you're comparing it to does. You have to be able to say 1 over n squared, which converges. Because remember, the limit comparison test doesn't give you different responses for convergence and divergence. It's always if you get a positive real limit. And so what that means when it's positive and real, it means they're behaving the same way. So if you compare it to something that diverges, it will behave like a diverging. If you compare it to something converge, it will behave like a converging, right? The ratio and the root test do give you different responses when you compare them, right? If it's greater than 1, we know it diverges. If it works out to be less than 1, it converges. And if it equals 1, you have to try another test because it's inconclusive. So on the back of here, right, remember, for those of you, we saw this handout before, all of those questions on the front page, I've got it labeled of which rows of the table right, the questions correspond to, and it tells you all the conditions of convergence, so it's just a good summary. So I would just have, the goal is when you're studying, you should just have this out with you all the time. It's just your quick reference guide. And if you just look at it a lot when you're studying and you reference it a lot, it will seep into your brain and you will memorize it. And if you're a visual learner like me, I will actually be able to picture in my head whole sections of this thing just because I stared at it so much when I was taking the exam. All right, what else? Yep. No, because I can usually see what test you're doing. I mean, try to be neat and clean with your work. If you are nervous, Nelly, when you take a test and you make a big mess when you write and you're worried I'm not going to be able to tell what test you wrote, it would be great if you wrote the test down. But the integral test is pretty obvious, right? There's an integral. The ratio test is pretty obvious. But yeah, if you can remember the name of the test, it would be awesome if you wrote the test down. But it's not like I'm not going to like just destroy you on points if you do an integral and don't write integral tests. Like, that's not gonna upset me. Yeah.
Is there a difference between absolute convergence and regular convergence?
So there's absolute convergence and conditional convergence, right? So if you take the only reason you would ever need to test for absolute convergence is if you have an alternating series, right? So if you take the absolute value, right, remember it just wipes out the -1 of the stuff. So if you take the absolute value and the thing converges, well, then we know all forms of that series will converge. So that's what I mean by absolute convergence. So all P series where P is greater than 1 absolutely converge, because if you can take all their positive values and those converge, the alternating will converge as well. So if you have an alternating P series, right, and P is greater than 1, the absolute convergence test is a really nice shortcut to test for convergence, right? But the alternative to that would be the harmonic series. The harmonic series 1 over n diverges, and we can prove that by using the integral test. You can actually see when you integrate it, it diverges. But when you alternate it, you're reducing the sum, you're slowing down the growth of the series, and that will actually converge. So the alternating harmonic series is conditionally convergent. The condition is that it's alternating, okay? And then we also showed that all those P series between 0 and 1, right, they diverge when they're positive, but they converge when they're alternating. So those are all conditionally convergent, and the condition is that they alternate. Yeah. All right, we'll tweak this down a little more. I see people putting on coats and shivering. All right. What else? Yep. No. Because if I just say, does it converge or diverge, I just want you to test what's in front of you. Make sure for the alternating series test, that was the one we didn't mention before, right? If it's not, because the alternating series test will work, you can technically use that for any alternating series, but make sure you know the 3 conditions, because you have to show the 3 conditions if you want to use it. And if you're trying to show that the harmonic series, the alternating harmonic series converges, you can't use the absolute test, right? You'd have to show me using the alternating series test. So just make sure you know those 3 conditions. Yeah.
Can you show an example of that?
A telescoping series? Yeah. All right. It's hard to make these up on the fly, but I think I got one. All right. All right. We got to make sure I do my subtraction the right way. Yeah. Okay, so I see the difference of 2 things, so that's a big clue that I might have a telescoping series. So one mistake on this, right, is this would be something that someone would try to be clever and they would mess themselves up, is they would be like, oh, well, I can separate these 2 series, and I can say, well, that's the harmonic series, and that's just another version of the harmonic series, and so I have the difference of 2 diverging series, right? Which is technically true, but that's not what's happening here, because we're separating them, so things are going away. The other thing people would do that would be completely wrong is if they separated them and they said, oh, well, this is infinity, so it just goes to 0, because infinity minus infinity is 0. That is complete bullshit, okay? Because if something's growing at twice the rate of the other, you're taking like something twice as big and reducing it, it could still end up at infinity. So please don't do infinity math, and it like really makes my head explode when I see people try to plug infinity into things. I just like, you're not allowed to do that. All right, so if we listed out the first couple terms of this series, well, when we plug in 1, we're gonna get 1 minus, right, 1/2. When I plug in 2, I'm gonna get 1/2, right, minus 1/3, and I'll go 1 more, and I get 1/3 minus 1/4. And then when I get to the nth term, right, and we would keep going. But if we look at this negative 1/2, right, cancels the positive 1/2. And then the negative 1/3 is gonna cancel with that 1/3. And then if you are following the pattern, we know the 1/4 will get canceled with the very first part of the next term. And then when you get to the nth term, well, we can see that 1 over n should have gotten canceled by the term before it. So if you want to find the sum of this series, it's simply equal to the infinite limit of 1 minus 1 over n plus 1. Because the only thing that didn't go away at the beginning was the 1. Everything in between got canceled, and that n plus 1, wherever you stop, it can't be canceled until you do a term after it. So that's why we keep that guy. And so when we can see, when we look at this limit, the limit of 1 is 1, the limit of this is 0, so this thing actually sums to 1. And so just like a telescope, all the intermediary things should drop off. Now, there are some telescoping series where the pattern's a little funky, like you got to go 2 or 3 terms before you start canceling stuff back, right? So that's why I said you want to list out a couple of terms, and notice I group them term by term so I can see the end, because you got to find that pattern of cancellation. All right, but yeah, anytime you have something being subtracted, there's a really good chance that it'll come out. And so we did one in class where we were only getting odd denominators. We did one like this where we were counting up. But you can see here, this is a convergent series, and not only is it convergent, I can sum, so trying to separate it and get clever with harmonic series would have just gotten you in a really weird place. It wouldn't have helped you at all. All right. Well, I don't know what you don't know. Hey, what's up?
Can you do a specific problem? Sum from 1 to infinity. N over negative 2 to the n minus 1.
That? Oops. That? Did I write it right?
Yeah.
Okay. All right. Wow, it's hard to read these out loud. Good job. Okay. So if we wanted to look at this guy, all right, I can probably feel okay about the idea that this thing probably stands a better than average shot at converging, just because I can see that you've basically got an exponential on the bottom and a linear term on top. So I definitely know the limit of this is going to go to 0, and it's probably going to get to 0 fast enough that we're going to be okay. But in order to test this for convergence, we need to do a little bit of rewriting up front at first, okay? So what I would do is, I don't want to deal with the negative 2. So what I can say is, we can say, we'll leave the n alone for a second. I can take this negative 2 and I can say, well, that's actually negative 1 to the n minus 1 times 2 to the n minus 1. And now I can see, well, this would be a really good candidate for the ratio test, right? So when you do the ratio test, remember we take the absolute value. The ratio and root test test for absolute convergence. So if I want to do the ratio test, and remember, the ratio test works great when things are moving really quickly. So when you have exponentials, factorials, and you're comparing that to something linear, it's like a really fast race to the bottom. But remember, we did one where we had 2 linear terms, and we tried to do the ratio test, and the answer came out to be 1 because they were just moving at the same speed, essentially, and we just couldn't distinguish between the numerator and denominator. All right, so if we look at this, right, we want to take the limit as n goes to infinity of the absolute value of the nth plus 1 term. So when I take the absolute value, I get to ignore all of that right there, right? Because the absolute value just wipes out the negative 1 of the stuff. So we'll have n plus 1 over 2. So when I plug in n plus 1 here, I'm going to get n plus 1 minus 1. So that just becomes 2 to the n. And then we'll divide it, right, by the nth term. So that's 2 to the n minus 1 over n. So the reason I drew the absolute value bars on the first step is because I wanted to show that I was legitimately removing the negative ones. All right. Now, nothing else in here will ever be negative. So then what I want to do is let's regroup the terms. So let's put the n's together. And let's put the 2's together. So 2 to the n minus 1 is 2 to the n times 2 to the negative 1 over 2 to the n. The 2 to the n's cancel. And so now I'm left with n plus 1 over n times 1/2, right? Because 2 to the negative 1 is 1/2. So what's the limit of the stuff in here? 1. So this limit is 1/2. That is less than 1. So this series converges. Yeah.
Those could be like a really simple question. I'm just kind of looking at. For power series, when you have the absolute value of x is less than r, how do you come up with your endpoints?
How do you come up with your endpoints? So,
there's usually like a number with it. It would be like x minus 3.
right, so what would the C be if it's just the absolute value of x?
It would be 0, right?
It'd be 0.
So what would your
So that means the center of the interval is 0. So if you have, so what he's saying is this, right? So let's put some real numbers here. Let's say we have x, I'm going to write the 0, is less than 3, okay? So that means the center of the interval is 3, the radius of the interval is 3, right? So if you think about that, well, if you measure 3 out from 0 in either direction, you're just getting -3 and 3. But algebraically, when you're dealing with an absolute value and you want to turn it into an equation, you're allowed to just take the expression inside and sandwich it between the positive and negative values. And then what you can do is solve that expression for x. So this is just saying x is between -3 and 3. So if I drew that out, well, there's 0, there's my center, there's r, right? And r goes from the center right out, okay? But let's do one where the center is not 0. So if I had an expression something like this, right? Say we're in this situation. Well, I don't really know exactly because the equation is supposed to be x minus some value c, not x over 2 minus some value c. So just like we said before, I personally prefer the algebra to do this. It just makes me more comfortable because I can see where I end up. So I can, just like I did before, I can take the expression and sandwich it between the positive and the negative values, because that's what the absolute value does. It says that stuff could have been -1 and turned into 1 when we took the absolute value, or that stuff could have just been positive all along. So then you solve the expression for x to get the endpoints. So if I multiply the whole equation by 2, that eliminates this fraction. So I get -2 x minus 8 to 2. Well, this is the same thing as the absolute value of x minus 8 is less than 2, right? You have x minus something is sandwiched between 2 of the same values. So the center here is 8, right? And the radius would be 2. And if I look at my endpoints here, right, I can finish this inequality off by adding 8 to everything. So I would get 6x to 10. So the middle of that is 8, and it is 2 spaces from each number. So when you draw this out on a number line, right, there's your center, there are your endpoints, 6 and 10, and you can see the radius is in fact 2 away from those. So you would have to then check the endpoints for convergence if we asked you to return the interval. So we know it's going to converge everywhere between these values. We just need to check. Now, if you happen to have a geometric series, okay, and you're doing the radius of convergence, remember, if it's a true geometric series, it can never converge of its endpoints. You still have to test and show me. But what should happen is when you plug in the endpoints, the R value should turn into 1. And 1 to the n is just going to give you 1, 1, 1, 1, 1, 1, 1, right? And -1 to the n is just going to give you 1, -1, 1, -1, all the way. And so, and then if there's an A out front, when you multiply that A times 1, if it's like 2, A is 2, you're just going to get 2, 2, 2, 2, or -2, -2. So geometric series, you'll find that they always diverge at their endpoints because when we test the endpoints, that's where the R value is 1, and the sum of a constant number has to diverge.
How do you know if the endpoints are brackets or parentheses?
When you test for convergence, you plug in the endpoints for X, simplify the series, and it should always simplify into something you recognize. Now, I will say this. If you are testing for convergence of the endpoints, and let's say you plug in X, and the whole thing simplifies down to 1 over n, I don't need you to run a test and tell me. You can just say, this is the harmonic series, it diverges. Okay? If it gets -1 over n, you can say, oh, this is the alternating harmonic series, it diverges. So when we're doing radius and testing for endpoints, I don't need you to see all the tests and all that stuff. But if I just give you a list of series and say test for convergence or divergence, that's when I need you to actually prove or show me what's going on. And when I mean prove, I mean run some kind of test and demonstrate. You got to justify your answers. Yeah.
You do a problem like kind of similar to the one on the quiz?
The last quiz problem we did? Yeah. We can just do that one if you want. All right. I'm going to hope this person wrote this problem down right, because I don't have it in front of me. -1 to the n, x to the n over the square root of n plus 1. Does that feel right? Let's check somebody else's. Okay, yeah, we'll go with that. I don't have those quiz problems memorized. All right. So yeah, this was your quiz 14 problem. All right, so we had the series from 0 to infinity of -1 to the n, x to the n over the square root of n plus 1. So the first thing that we do is we perform the ratio test, right? So for the ratio test, right, we want to get the absolute value of a sub n plus 1 over a sub n. So that is going to knock out the -1. So you're going to have x to the n plus 1 over the square root of n plus 2. And then when we divide that by the nth term, right, the fraction flips. So I don't even need to see the -1s, because that's what the absolute value does. It just takes them away. If you write them in there, you're going to get yourself in trouble. All right, so we want to take the limit of this expression as n goes to infinity. And when I go to take the limit, I'm just going to regroup these things. So I can say that this all goes under the same square root, right? Because something to a power over something to the same power. You can write it as everything to that power. And then this is times x to the n plus 1 over x to the n. So this is just x to the n plus 1 times x. And oh, sorry guys, you got to keep the absolute values around the x's, because those x's could be any value, positive or negative. So you're allowed to take them away from the n's, but not the x's. So this x to the n is going to cancel the x to the n, and I'm going to end up getting the limit of the absolute value of x times n plus 1 over n plus 2 under the square root. So for the purposes of the limit, n is the variable, not x. You get to treat the x's like they're constants. So the limit of the stuff under the square root is just going to go to 1. So this is just going to be the absolute value of x times 1. So that's what you get out of your limit. But for the ratio test to pass, because we're testing for convergence, in order to say that the ratio test was a success, right, the result of your limit must be less than 1. So that's how you get your expression that we then turn into an interval. So we actually just looked at this, right? And we said, well, what that really is saying is that x minus 0 is less than 1. So that means the center of our interval is going to be 0. So x is between -1 and 1. So I need to test the endpoints -1 and 1. So if I wanted to say what the radius of convergence is, the radius is 1. To give the interval of convergence, I can't do that till I test the endpoints. All right, so now let's test these endpoints. And this is where I was saying I don't need to see a bunch of tests run again when we do these problems. So if I take the original series, so let's start with x equals -1. If I take the original series, -1 to the n times -1 to the n over the square root of n plus 1. Did I mess up? Oh, okay. Oops, sorry there. Right? Well, this -1 and the -1, since these powers are the same, they're always going to become 1. So this is really just the series, because you always got to simplify it down, 1 over the square root of n plus 1. Well, that's basically just a p series where n is 1/2, or p is 1/2. Because if I drop the 1 here, right, the 1's going to be insignificant when you go to infinity, and that's basically just 1 over n to the 1/2. So if p is less than 1, we know this diverges. So this guy diverges. And so what I would say is, you don't have to do it, but you could say compare to p series where p is 1/2. All right, so I just need to know what you saw and how you're justifying that you knew that converged, okay? Yep.
Could you have done the interval test with that?
We're not doing an interval test. We're finding the interval of convergence. So when you find the interval convergence, you have to use the ratio test, and when you test the endpoints, you're just plugging in the x values and simplifying it down. And that's what I'm saying. The whole point is you shouldn't have to run any tests. You should be able to recognize what you're looking at. They will always simplify into something really familiar to you. And so that's what I was saying. I don't need to see another test because you've already run a ratio test, and now we're just testing the endpoints. All right. So if we look at x equals +1, but yeah, I mean, if that were the series on its own, you could use an integral test to test for convergence or divergence, but we're doing a interval of convergence example, right? So if x is +1, right, then we're going to have -1 over n times 1 to the n over the square root of 1 plus 1, or n plus 1, and the numerator is always going to be -1 to the n. So now what I've got is an alternating p series where n is, or p is 1/2 essentially. And so we know that those guys are conditionally convergent, right? They diverge when they're positive, but they converge when they're alternating. So this converges, right? Alternating p series, right, where p is 1/2. So the interval of convergence is this. So this is the parentheses bracket question. You use parentheses when it diverges because you don't include that value in the interval, and you use brackets when it converges because you do want that interval or a value in your interval. And you should always go back and double check that the center is the middle of the interval when you set up the final answer. And that's just, so there's little gut checks you can do along the way in the problem. So even if you're not right, you can make sure that you're wrong consistently. And usually what that means is you knew what you were doing. There was just some algebra step back along the way. And if I can see that everything kind of checks out and there was just one tiny algebra mistake, I'll ding you for the algebra mistake, but I don't compound your errors when I grade on exams. As long as it's like nothing major that just threw you off on a completely tangent. But if you just put a 1 instead of a -1 somewhere, but you correctly interpreted all your results and you perform the test correctly, I'm usually pretty okay with that. Because everybody, you know, I'm famous for 1 times 1 is 2 on exams. I've done that many times. Yeah.
So with any p series that diverges with the alternating region converge no matter what.
So the condition was, though, for that, remember, the p's had to be positive exponents because they had to be in the denominator. Because if you had 1 over n to the negative 2, that puts it in the numerator and becomes n squared, right? So we said any values of p between 0 and 1, right? When you alternate them, we did the alternating series test on a bunch of them. We saw they all conditionally converged. So it's a really important concept to know. So if you're recognizing some of these patterns, you can cite them, and it makes your work a lot easier. Yep.
When you're plugging in endpoints, you need to worry about what it converges or diverges to, correct? Just so we know if it diverges.
That's all we care about, yeah. Well, you can't know, right? That's what we said. The only 2 series that you can give that answer to are geometric and telescoping, right? Because, and that's the thing, that's why it's so unsatisfying. We start with sequences and we always know what it converges to. And for a sequence, you have to tell me what the value is it converges to because you take the limit and you can see the value, right? And that's what I'm saying is, what number does the list become as it goes to infinity? But for series, it's very unsatisfying because we never really get an answer most of the time. We just know the answer exists. And so we did a couple of examples where I said we can get in the ballpark. We know that it's somewhere around that value. So one of the big mistakes people make with the integral test is they try to say the result of the integral is the sum of the series. And I actually did a problem where I showed you that that wasn't really the case. The integral got you in the ballpark, but it wasn't exactly quite the sum of the series. So yeah, we're just saying converge or diverge. And for these types of problems, when you plug in those endpoints, you should recognize what it simplifies down into. It should simplify into something that we've seen, like a p-series, a geometric series, one of the more recognizable famous series when we do those. All right, what else? I always know on these days who's been thinking really hard about this stuff and who hasn't. Yeah, what's up?
Can you do are there any kind of rules or anything for reduction of factorials? Like where you got n plus 1 over the n for factorial?
You talking about like cancellation and stuff?
Yeah, because I'm real second.
Yeah. So one thing about factorials you want to make sure you do is you have to remember so there was a problem that was on WebWork and it was just really pissing everybody off. All right, and what it was is it was the product of all the odd integers, right? And everybody was trying to rewrite that, and then you would see like 1.3.5.7, and everybody kept trying to write that using a factorial, and you can't, because if you see the factorial symbol, it does not allow you to skip any consecutive integers at all. You're not allowed. So if you have something, right, like this, which we saw right in class, and this is really important because if you're going to do the ratio test, you have to know. Well, all this is, the numerator is saying go take n factorial, right, and then multiply it times one additional number. So we know the n factorial cancel, and all you get left with is n plus 1. But if you have something like this, right? Well, n plus 4 factorial is definitely bigger than n plus 2 factorial, but the numerator, right, leave the small thing alone. What the denominator is saying is go all the way up to n plus 2, but then the next number on the number line is n plus 3, because you just keep adding 1 to the previous digit, and then you have n plus 4. So if n was 2, for example, this is 4 factorial over 6 factorial. So it makes sense that you would have 5 and 6 left over when you cancel. So if you're having trouble seeing this, pick pretty small values of n and like work out and you can kind of see how many numbers you should have left over. So this would simplify down into 1 over n plus 3, n plus 4. Okay? So be real careful. And then we'll also remember we said there was a distinction between this notation. 2n factorial is read 2 times n factorial. But if I actually mean 2n factorial, we put it in parentheses. So if there's no parentheses, you just treat it like a normal coefficient. If you see 2 times n, so if n were 3, for example, this is 2 times 3 factorial. This is actually 6 factorial. Does that, wait, sorry, does that fix it? Okay, yeah, sorry.
Just kind of building off that. I remember seeing a problem that it was 2n factorial exactly like that, and then below it was 2n plus 1 factorial.
Wait, so was it like this?
Yeah, exactly like that one.
So it was 2n factorial over 2n plus 1 factorial?
Just like that, yeah.
Yeah, so that's just 1 over 2n plus 1. Because 2n plus 1 is one number past 2n. So this right here is 2n factorial times 2n plus 1. So if this were 6, this is 7. Yeah.
Would it work the same way with subtraction? Like, would we ever get n minus 1 factorial? Something like that?
Yeah, actually, yeah. So that's actually a good question. So if you had n factorial, right, over n minus 1 factorial, right? Well, now n factorial, you look at the bigger thing, right? You always want to break up the big thing. So n is bigger than n minus 1. So this is saying go up to n minus 1 and then multiply by n. So this just simplifies to n. So you're always going to take the larger factorial and go up to the smaller one that you have and then figure out, well, how many numbers beyond that do I have to keep going? And then you just add those on at the end. And so if you saw this with numbers like 3 factorial, right, over 5 factorial, right, that's 1 times 2 times 3 over 1 times 2 times 3 times 4 times 5. So if you go back up to this example, this is what I've done here. The 3's canceled and you ended up with 2 more numbers on the bottom that you had to count. So remember, the factorial does not allow you to skip any consecutive digits. So if you had 2n plus 3, then that would have been 2n factorial times 2n plus 1 times 2n plus 2 times 2n plus 3. Because you have to count every digit to get up there. You're not allowed to skip anything. So remember, factorials are the most exciting thing in math. So have you guys ever been to Walgreens and seen like their store brand food? It's only their food because, you know, like everybody has their own store brand. So this like kills me. All the Walgreens store brand food items are that. They're nice with an exclamation point. And so it's on like, so whenever I walk around in there, I'll take a photo and I'll send it to like one of my friends and I'll be like, I got you some nice peanuts. And then it'll be like, nice cashews. And like, and when my cousin comes to visit, I always buy her a bag of something nice and leave her a note that I wanted to get her something nice for her visit. But yeah, next time you go in there, look at that. It'll crack you up. But you go to the food aisle and just be like, nice salt. It's always like so excited. And then on the water bottles, it's like embossed on the bottle. So yeah, so we always have a good time. But I always try to find the weirdest thing I can with nice on it and send it to my friend. But, all right, that's it. You want to call it? All right. I'll be at Millage till 9. We have our own little corner just for Calc 2, so. Save me from the lower level math kids, they'll drive me nuts.
What did you say that you were going to do beforehand? You said something about, what was it called? Rankin.
Oh, I didn't mean to say Rankin. I meant Millage Hall. Rankin's the athletic. I used to work at Rankin in undergrad. I've worked at so many tutoring places. No, I always say Rankin when I mean Millage because Rankin's were the athletes. I used to tutor the athletes, yeah.
What's room number?
It's just, when you walk into Millage, it's just the Millage Hall Math Lab. So when you walk in, you just go to the right, and you'll see a little kiosk where you sign in, and you just follow it around. But there is no room number. Yeah.
See you there.
Yeah.
Yeah.
Or chapter 6, I was looking at it and only page
So
it said like 1 out of 2 on the bottom of the page and there were only 5 questions. And the second page wasn't there.
oh, it's only 5 questions.
Okay,
So
I was
it
just gonna make
okay.
sure.
So yeah, the page numbering at the bottom of the document, I forgot to check the footer, but it's only 5 questions. But if you look, one of the questions is like four problems in that one question, so it works out to be I think like 9.
Okay, because
Yeah.
I thought you were like.
And I
it's
do
gonna be
need
10
you, like you'll
questions.
see, like if
Just
you
to
look
make
at the
sure.
test, on some of those types of questions, I had them set up but not evaluate. But because this is like a take-home set, just make sure you know you got to complete all of the intervals because y'all need to practice integrating. And then I worked all the ones out to completion on the video, and then you can also go back and look at all the quizzes and stuff too, and I always worked all of those out to completion if you need to look at more practice problems. But yeah, I tried to make sure they weren't too nuts. They were pretty basic stuff, yeah.
Easy question. What is our, I don't know if I